For over a century, our world has been powered by a single standard, alternating current, or AC. It was the victor of the legendary War of Currents between Nikola Tesla and Thomas Edison. But today, a quiet revolution is happening. The winner of that 19th century battle is being challenged by the very thing it defeated: direct current. But this isn't your grandfather's DC. We're talking about high voltage direct current, HVDC. It is the only technology capable of carrying the massive amounts of renewable energy we need across continents. From the deserts of China to the North Sea, HVDC is becoming the clean energy highway of the 21st century. In this deep dive, we'll explore why the physics of AC is failing our modern needs, the trillion-dollar business supercycle driving this change, and the engineering marvels that make it all possible. Why did we choose AC in the first place? Because 100 years ago, it was easy to step up to high voltages for transmission and step down for homes using simple transformers. DC couldn't do that, but AC has a distance limit. As AC travels through a wire, it creates a magnetic field that pushes back against the current. This is reactance. It also suffers from the skin effect, where electricity only flows on the outer surface of a wire, wasting the core. In long subsea cables, AC creates so much charging current that it can't travel more than 50 to 100 kilometers before the cable essentially clogs up with its own reactive power. This is where HVDC wins. DC has no skin effect and zero reactive power loss. While an AC system might lose 19% of its power over just 150 km, an HVDC system stays steady at around 4%. In fact, for any distance over 800 kilometers for overhead lines or just 50 kilometers for subsea cables, HVDC is the only efficient choice. To use DC, we need a way to turn AC into DC and back again. This happens at converter stations. For decades, we used line commutated converters, or LCC. These are the heavy lifters using thyristors, essentially giant digital switches. They are incredibly robust, capable of handling over 12 G dollars of power, enough to power 50 million homes in a single link. But they have a flaw. They need a strong AC grid to guide them. If the AC grid fails, the LCC fails. Enter the new king, voltage source converters, VSC. Instead of thyristors, these use IGBTs, insulated gate bipolar transistors. VSCs are smart. They can create their own AC frequency, meaning they can restart a dead grid, a black start. This makes VSC technology the dominant choice today, holding over 53% of the market share. And the latest evolution? Modular multi-level converters, or MMC. Instead of one big switch, we use hundreds of small submodules. It's like building a perfect wave out of Lego blocks, resulting in a nearly perfect sine wave with almost zero electrical noise. This isn't just an engineering story. It's a capital explosion. We are in a capital investment supercycle. In 2024, the HVDC converter market was valued at $17 billion. By 2030, analysts expect this to reach up to $22 billion. Who are the players? It's a consolidated big three in the West: Hitachi Energy, Siemens Energy, and GE Vernova. But the real giant is the State Grid Corporation of China. They have built over 20 ultra-high voltage projects, including the Mount Everest of power lines. Let's look at what the pinnacle looks like. The Changji Guquan project in China is a record breaker. It operates at plus or minus 1100 kV, the highest voltage on Earth. It stretches 324 kilometers from the remote, wind-swept Xinjiang region to the industrial hubs of East China. It carries 12,000 RTM. To put that in perspective, that's the equivalent of 12 large nuclear power plants. This single line reduces coal consumption in the East by 38 million tons every year. If the tech is so good, why isn't it everywhere? The answer is policy and risk. In the U.S., projects often die because they cross too many state lines. To fix this, the Department of Energy has created NICEs to allow the federal government to bypass state-level blocks. In Europe, the 10-year Network Development Plan mandates that every country must be able to import at least 15% of its power by 2030. But it's risky. The X-Links project, meant to bring solar power from Morocco to the UK, was rejected due to cumulative risk. Even Sun Cable's massive Australia-Asia link faced a voluntary administration after internal funding clashes. The ultimate vision is a global supergrid. Proposed by GIDCO, this roadmap envisions a worldwide energy connection, where the sun shining in the Sahara can power a cold winter night in Europe or wind from the Gobi charge cars in Tokyo. By 2050, they envision 9 vertical and 9 horizontal energy channels connecting the entire planet. We are moving toward a world where electricity is a truly global commodity, just like oil is today, but without the carbon. To get there, we need to solve the interoperability problem. Right now, you usually can't mix different brands on the same line. But initiatives like Sigri's working group are pushing for partially open software to make different brands finally talk to each other. Most of us will never see an HVDC converter station. They are tucked away in remote deserts or hidden in offshore platforms. But every time you turn on a light using renewable energy, there is a high probability that HVDC was the invisible hand that brought that power to you. It is the bridge between our carbon-heavy past and a sustainable electric-centric future. The currents are changing, and this time, Edison might finally get his revenge. If you enjoyed this deep dive, hit the subscribe button and let us know. Do you think a global supergrid is actually possible? Thanks for watching.